Right guys, let's have a look at question 7. I've drawn the picture in advance, but let's just go back and have a quick look at the question from the paper itself. Question 7 then. Here it is here. We've got this rod AB, uniform rod. It's of mass 3 kilograms and length 2 meters. So I've put that in the diagram. There's 2 meters. Because it's uniform, the mass of 3 kilograms, it's like, as far as the center of mass is concerned, it'll be in the middle, won't it? 1 meter either side, and it'll be 3g as a force acting downwards there at its center of mass. The particle of mass 5 kilograms is attached at A, so that's 5g acting down there, isn't it, as a force, and 2 kilograms, so 2g acting down here is at B. The diagram shows the rod horizontally and in equilibrium on a smooth support at point C, where AC is x. So this distance is x, and we know there's going to be a reaction here acting upwards to hold it in equilibrium. So calculate the magnitude of the reaction at the support at C and the value of x, which was this distance here. So let's go back to our problem now. Now we've read the question. Here's all the things. We've got to put the forces in. So as we said, there's a force acting down of 5g here, this due to this mass. There's a force acting down of 2g for this mass. This rod here is uniform of 3 kilograms. Center of mass will be in the middle, so that's 1 meter either side. So that's why I put 1 meter in there. Acts down with is 3 kilograms in weight, so its center of mass has a weight acting down of 3g at its center of mass, so to speak. This distance here is x. If this half is 1 in total, which it is, then this distance must be 1 minus x then, mustn't it? So let's resolve the forces. Apply F equals ma in the vertical direction, and let's see what we get. Don't forget there's one more force to put in, which is the reaction force of what it rests upon here in equilibrium. So that's an R there. So maybe I ought to write that a bit more clearly. It's an R. Okay, so that's the reaction force there. So applying F equals ma vertically gives, so the forces downwards then, first of all you've got R minus the 5g minus 3g minus 2g, because they all act down, don't they? That's all the forces then, equals mass times acceleration. Acceleration is 0, so that tells us then R is equal to 5 plus 3 plus 2 is 10, 10 lots of g, so R equals 98 newtons. That's our reaction force then. Now let's take moments around C, because it's in equilibrium. So take moments around C in that direction, in the clockwise direction. So we've got 3g times the 1 minus x, haven't we? Force times distance. And then here we've got 2g, and its perpendicular distance is 1 plus 1 minus x, which is 2 minus x. So you've got 2g, and it's 1 plus 1 minus x, which is 2 minus x, yeah? So that's that. And then you've got, we're looking in the clockwise, so this is anti-clockwise, so you've got minus 5g times the x. There we are, that's that force, and that force. The R goes through the point itself, so that won't affect the problem, it'll be 0. So that equals 0 then. So there's your moments. So what have we got? So let's expand the bracket then. We've got 3g minus 3gx plus 4g minus 2gx minus 5gx equals 0. So are we all happy that that's 10g? There's a g all the way through, so the g's can cancel. We've got 3x, 2x, and 5x is 10x minus 10x, so I can write that over there as 10x. So it's that one, and that one. And then the g, the 7g, so that would be 7, wouldn't it? So what does that tell us then? Divide by 10 both sides, 0.7 meters. So there's x. So we've got the reaction force and the distance x. Let's go back to our question to make sure we've answered it. Or calculate the magnitude of the reaction of the support at C and the value of x. Yep, that was it. So we've got 98 newtons, and we've got a distance x of 0.7 meters. Okay, I think we're dealing with meters here, though I'm not sure that it actually said that in the question. Quick look. 2 meters, yeah, we're in meters. Okay, good. So that's question 7 done then. Great. Let's go on to the next question, question 8. Good.